Hello everyone. In today's discussion, we discuss a very interesting question from the CSIR UGC Net Mathematics June 2025. And this question is asked from the measure theory part. Here in this question, mu denotes the standard Lebesgue measure on the real number set R. And f is a non-negative measurable functions. Measurable function means it pulls the measurable set to the measurable set, and this measurable function is defined on the real number set. And there is a sequence is given. It is an unbounded sequence. Unbounded means when n goes to infinity, an goes to infinity, and a0 is equal to 0 is given, and this sequence satisfies this relation an plus 1 is less than equal to c times an, and for some real number c. Okay. And this set AKs are defined in this way. Clearly this set AKs are what? Disjoint set. You can verify it by yourself. And this set AK is also measurable. Why? Because AK, this set is nothing but the inverse image of f inverse of AK close interval and AK plus 1 open interval. And we know that every interval means it may be open, close, or half open or half close. All these are measurable sets. Since our function f is measurable, so it pulls measurable set to measurable set. So the f inverse of this set will, since this is measurable, MSBL measurable, so f inverse of this set is also measurable, and this set is nothing but AK. So every set AKs are measurable. Okay, I hope this concept is clear to you. And in this question we have to verify these four options. In the first option is saying that if f is Lebesgue integrable means integration over r f of x mod dx, this should be finite. But in our question our f is a non-negative function, so there is no need of modulus, so f of x dx should be finite. It is given. Then we have to show that this series is finite, means we have to check. Okay. And in the second option it is saying that if this series is finite, then f is Lebesgue integrable. And in the third option is saying that if this series is finite along with this condition, then f is integrable on R. In the fourth option we have to check if this series is finite and f is bounded, then f is integrable. So we have to verify these four options. First we will verify the option 2 and option 4, because these are easy to discard. Means option 2 and option 4 are false. For that reason we have to create a concrete counter example. So to create a counter example, we consider this sequence a0 is equal to 0 and a1 is equal to 2, and AK plus 1 is defined in this way, is equal to 2AK for k greater than equal to 1. K greater than equal to 1. Then clearly this sequence satisfies this strictly increasing property, and it is an unbounded sequence, and it is also satisfies this thing an plus 1 is less than equal to an, because our an plus 1 is equal to n, so it can also be written in this form. Okay. Then we will define the constant function f of x equal to 1 for all x belongs to the real number set. Then if you calculate the value of the a0 set is nothing but this one. Okay, it is coming from this definition. Okay, if you calculate these things, this implies that x belongs to the real number set, f of x less than equal to 2, but we know that f of x equal to 1, so this relation is true for all the x. So means it implies what? It contains every real number set, so a0 is equal to the whole real number set, and we know that these AKs set are disjoint, so the rest AKs will be what? Phi for all k greater than equal to 1. So if you calculate the sum of this series is nothing but 0 into measure of a0, and but a0 is equal to what? The real number set, and a1 times measure of phi, measure of a1, it is all phi, a2 times measure of a2, but a2 is a phi set, so it gives these things. So it gives 0 0, because the measure of the phi set is 0. Okay, but here this quantity can be written in this form 0 into infinite. 0 into infinite, but we know that 0 into infinite is equal to 0. At this point, do not confuse that 0 into infinite is a indeterminate form. This quantity is not indeterminate form because it is not in the sense of limiting sense. If it were in the sense of limiting sense, then you can say that it is an indeterminate form. But in the case of measure theory, it is a standard convention that 0 into infinite is equal to 0. This you can note these things. This convention is taken in every measure theory book. If you know more about why this convention is taken, that 0 into infinite is equal to 0, I have attached a stock exchange link in the description box. You can check it. Okay, for the time being, believe me that 0 into infinite is equal to 0 in measure theory. Okay, but in the limiting sense it is not true. It is called the indeterminate form. Okay, so this summation value is equal to 0. So this series of this value is equal to 0. Equal to 0 means what? It is a finite quantity. Okay, now we will calculate the value of the integral. The value of the integral is what? Since f of x is equal to identical equal to 1, so it gives this one, and this is nothing but the 1 times measure of the real number set, but measure of real number set is infinite, so it gives infinite. So we create a counter example in which this series is finite. It is finite, but it is not Lebesgue, but f is not Lebesgue integrable. This value is infinite. What means f is not Lebesgue integrable. Lebesgue integrable. So we create a counter example these things. So let us verify the option 2 and 4. Option 2 is saying that if this series is finite, in our case this series is finite, then f is Lebesgue integrable, but f is not Lebesgue integrable in our case, so option 2 is false. And option 4 is saying that if f is bounded, but we have taken the function f equal to 1, identical equal to 1, it is a bounded function. In this case also this series is finite, but f is not Lebesgue integrable, so option 4 is also false. Okay, now let us verify the option 1 and option 3. These two are the correct option. First we will verify the option 1, means we have to prove this option 1. In the option 1 we have to prove what? We will take that f is Lebesgue integrable. Option 1 is given that f is Lebesgue integrable, then we have to show this series is finite. Okay, we have to prove this thing. Okay, let us proceed to prove the option 1. Option 1 is explanation of the option 1 starts from here. Okay, given that f is Lebesgue integrable, okay, means what? The integral of f of x modulus, but here since f is a non-negative quantity, there is no need to put modulus here. Okay, so this thing is given finite. Okay, since f is Lebesgue integrable. And the definition of the Lebesgue integrable is this one, Lebesgue integrable. It comes from the definition. If you do not know, then check in any measure theory book, you can find it. It is the integral, supreme value of the integral of the simple functions. I hope that you all know about the simple functions. Simple functions means it is a measurable function whose range set contains finite number of elements. Okay, it is the definition of the simple function. If you do not know, then go through the any standard measure theory book, then you can find it. Okay, so it is the standard definition of the Lebesgue integration of a non-negative function in terms of simple function. So it is the supremum value of all the simple function which satisfy this condition: 0 less than equal to s less than equal to f. Then you take the supreme value of all these simple functions of this type of integral, then you can find this integral value of f. Okay, so this thing is given to you, but our target is prove that this series is a finite quantity. Okay, so this series is finite quantity. How can you show this? We can show that the partial sum of the series is a convergent thing, or partial sum of this series. Partial sum means what? K from 0 to n, this a0, right, let me write the whole thing, a0 mu of a k, not a, here I have written wrong, it is a k AK measure of AK. Okay, so it is not A0, it is AK measure of AK, and this is the partial sum. If we can show that this partial sum is bounded by something for every n, means this partial sum is bounded, means partial sum is bounded means what, then this series will be convergent. So it is our target. So to achieve our target, we define these simple functions. These are the simple functions, and here 1ak is a nothing but the indicator function, or called the characteristics function. These are the indicator function, function. Okay, it is called the indicator function or characteristics function. It is defined in this way. 1 akx is equal to 1 if x belongs to the set ak, and 0 if otherwise, and these sets ak's are the these set. Okay, here I am taking this set ak's. Okay, I hope that you remember the definition of the ak set. Okay, by using this set ak, I am defining the indicator functions, and by using these indicator functions I define this set s0, s1. These are not set, these are the function. This is a s0 function, it is a s1 function, it is a sn function. Okay, and these ak's are 1 ak's are indicator functions are defined in this way. Clearly this set sn is a simple functions. I have already told that simple function means the range of the set contains finite number of terms. Here the s0 set, range of s0 contains what? It gives a0 or 0, these things. If in the similar way, if you calculate the range of s1, you can find it is a0, a1 or 0, these things, not a0, a1, 0. Okay, why? Because these sets are disjoint set. You cannot, one can think that why a0 plus a1 is not coming, because x can lie either in a0 or lie in a1, or it may do not lie in a0 or a1. Okay, means that there are two possibility, means either x lie in a0 or a1, or it may also happen that x neither lie in a0 nor lie in a1. But it is not possible that x is lying in a0 as well as a1, because these two sets are disjoint. I have already told these set ak's are disjoint. So the range of the set contains range of the set s1 can be this one. So all these sets are finite sets. So these s0 sn functions are simple function. So one criteria is fulfilled to apply this thing, this definition. But next we have to verify that it is a non-zero, non-negative quantity. Clearly these functions are defined in terms of indicator function sn, and we know that these small ak's are also non-negative quantity. It is given in our question itself. Okay, a0 is 0, and these are the all non-negative quantity. So these functions are, so these sn functions are simple and non-negative. Next we have to verify, ensure that this sn satisfy that sn less than equal to f. We have to verify this thing. Okay, and this is the definition of the sn. So let us prove that this snx is less than equal to f of x for all x belongs to a real number set. If you take the x, if you take this type of x, means if x does not lie in this set, then the value of snx is equal to what? 0. It comes from the definition, because it does not lie in any ak's. So since one ak is the indicator function, so it gives 0 sum. Okay, but since fx is non-negative, so 0 is less than equal to f of x. So in this case it is true, snx is less than equal to f of x. Now let us check the other case. This the rest case is this one. If x lie in this union, if x lie in this union, then x lie in ak, in some ak, but it is in some exactly 1 ak. Exactly 1 is coming due to then these sets ak's are disjoint. Okay, so this the value of the snx at the point x gives ak because it is lying in exactly 1 ak. Okay, and from the definition of the ak set is defined in this way. On if x belongs to ak, then f of x is dominated by a k plus 1 and it is greater than equal to ak. So this implies that f of x is greater than equal to strictly not strictly, it is greater than equal to ak. So from 2 and 3, if you combine 2 and 3, you will get that snx is less than equal to f of x when x belongs to this union. So in this case also it is true. So from 1 and 4, if you combine the inequality 1 and inequality 4, you will find that snx is less than equal to f of x for all the x belongs to the real number set. Therefore star okay, so we can create a sequence of simple function which satisfies all these property of this star. So from the star, but here if you observe that here the supreme value is over all the s, but we are taking a particular sequence, so this integral value will be dominated by this quantity. Means I am saying that this is true because this quantity is the supremum over all the simple functions, but we are taking a particular case of these things. So this value is bounded by the supremum of this supremum value. So this is true, this quantity is bounded by these things. Okay, and the definition of the snx is in terms of this one. This is the definition of snx. Okay, so it gives this and here this summation is a finite sum. Therefore summation and integration is interchangeable, so there is no problem since it is a finite sum. If it were infinite sum, then you have to think whether you can apply dominator convergence theorem or Fato's lemma, all these things, but here there is no need to apply anything because it is a finite sum. Okay, so it can be written in this way. And this indicator, if you integrate this indicator function, this is nothing but the measure of ak. Okay, why? Because this integration can be written in this way: r intersection ak into 1 dx. Okay, and this gives nothing but ak, so it gives the measure of ak. Okay, so I hope that it is clear. Means it is a very simple exercise question. You can calculate these things. It is gives the it directly comes from the definition of the measure of ak. In measure of ak can be written in this form, in this integral form. So it gives this value, and this value is bounded by this, and we know that since f is Lebesgue integrable, this quantity is finite, and this relation is true for all the n. So we established that the partial sum value is bounded by a quantity which is independent of n. And if you take this sum as a partial sum gn, suppose, because we have already used the Sn, so we cannot take Sn here, so we are taking gn. This sequence gn is an increasing sequence. When if you increase the n, since these summations are the non-negative, this is the summation of the non-negative quantities, so when n will increase, this summation value will increase. So clearly gn is a monotonically increasing sequence, and it is a bounded above by this integral value. Okay, so therefore it is a convergent quantity. Why? Because we know that from the standard real analysis, if a sequence is monotonically increasing and it is bounded above, then it is convergent. Therefore this sequence gn converges to some real number. Okay, gn converges to what? Converges to a real number. So therefore this series is convergent. Okay, means when gn goes to infinite, when gn comes to c, means when n tends to infinite, but when n goes to infinity, this gn value is nothing but this series. So it implies that this series is convergent. Convergent means what? This value, summation value is finite. Okay. Therefore, we established that when f is Lebesgue integrable, this value is a finite quantity. So we verified that option 3 is option 3, not option 3. It is the option 1. If f is Lebesgue integrable, we established this thing. Next, we will prove that option 3 is also true. But the condition is that this series is finite along with this quantity. This quantity will help us to prove that f is Lebesgue integrable. Okay. So let us verify the option 3. Option 3 is here. Okay. Here there are two things are given. First is given that this series is finite, and second thing is this one. And this thing helps to infer this one. This implies that a zero set is a phi set. Why? Because the definition of the a zero set is defined in this way. But we know that our f of x is greater than or equal to a1, but it is saying that f of x is strictly less than a1. So there is no x such x, because our f satisfies that f of x is greater than or equal to a1 for all x belongs to R. But it is saying that it contains a zero set contains all the points for which f of x is strictly less than a1. So there is no such point. Means what? A zero set is a phi set. So measure of a zero is equal to what? 0. Okay. It will be used later. But our main target is to show that this integral value is finite. Means f is Lebesgue integrable we have to show. So we have to show that this integral value is finite quantity. But we know that if you take the union of all the AKs, what it gives? What? The real number set, and these all AKs are disjoint set. Keep in mind that these all AKs are disjoint and their union gives the real number set. Okay. So we will start from this integration, then we will show that this integration value is finite. But we know that the real number set can be written in this union form. Okay, union of the all AKs, and these AKs are the initial AKs which are defined in the in our question. Okay. And since these sets are disjoint, then this union value can be written in this summation form, because in this summation form, okay, then we will apply the definition of AK. AK is what? On the set AK, it contains all the real numbers set, all the real numbers, so that it satisfies AK less than or equal to f of x strictly less than AK plus 1. So if you observe the definition of the set AK, you can find that fx value is always less than or equal to AK plus 1, but on the set AK. But here our integration is over AK. So here this fx can be dominated by AK plus 1. So in the next step we remove that f of x by AK plus 1. So there is less than or equal to sign is coming. Okay. So I hope that it is clear. Now and AK is a constant quantity, so it comes out, and the integration of AK dx is nothing but the measure of AK. Okay. So it gives this thing. At this point one can apply this relation, but be careful, we cannot apply this relation directly. Why? Because this relation is true for the k greater than or equal to 1, but our k is ranging from k from 0 to infinity. Here k equal to 0 is will create a problem, so we have to remove it first. Okay. So this sum can be written in this form: a1 times, if you put k equal to 0, it gives a1 measure of a0 plus this sum. On this sum we can use this relation. Okay. So here we have used this relation, but in the previous part we have already calculated the measure of a0 is equal to g0. So we put this thing, so we get this 0 value. Okay. Now we have reached to this step, and here c times ak, c is a constant quantity, so it comes out, so it gives this sum. But in our question given that this series is a k from 1 to infinity or k from 0 to infinity, ak is a finite quantity, but our c is a real number, so their product is also a finite quantity. So this gives a this is a finite quantity, but we have started from here the integration value and reached that this integration value is dominated by some finite real number. Okay, this implies this quantity is a finite quantity. This implies what? F is Lebesgue integrable, so it is true. So option 3 is true. I hope that you all understood it very well. Thank you all. Bye bye. See you next time very soon.